Okay, good morning everybody. It's my role as Programme Chair for RSS 2015 to welcome you all to the southwest of England. It's the first time that the conference has been in the southwest of England for 13 years, I think, till we went to Plymouth 13 years ago. And we had fantastic weather there, just as we're having now, so it never rains in the southwest of England, as I'm sure our plenary speaker will agree. So welcome to the sunny city of Exeter. I hope you enjoyed the welcome reception last night, those of you who were able to attend. And we have three fun-filled, action-packed days ahead of us. We have a slightly different way of running the RSS conference this year, with themes running across all 3 days. So hopefully there is something for everybody amongst those themes. I'm also here to introduce our first plenary speaker, and so we're going to begin our proceedings with a presentation from Professor Dame Julia Slingo. Now, Julia is the Chief Scientist at the Met Office and also Visiting Professor in Meteorology at the University of Reading. She started her academic career, or at least her studies, in the southwest of England at my own institution, the University of Bristol, where she did her BSc and her PhD. And actually, the only other time I've ever met Julia, when I say met, I was part of the procession at graduation, because Julia is an honorary graduate of several institutions, including this one, and she's also an honorary graduate of Bristol. And at Bristol, when we have an honorary graduate, basically somebody stands next to them and goes on and talks about all the wonderful things they've done, and they don't get to say a word, they just get presented with a degree. So this is my opportunity to hear Julia speak for the first time and welcome her. And her talk will be on chaotic but not random, uncertainty in weather and climate prediction.
Thank you very much. Yes, so a bit daunting coming to talk at the Royal Statistical Society, because I'm not a mathematician and I've always struggled with statistics. I thought, well, what shall I talk about? But actually, one of the things that, of course, you will hear time and time again is that they got the forecast wrong. They didn't know what the summer was going to be like. They're so uncertain about climate change. Why should I believe any of it? And I thought, well, actually, it would be really good to talk about the fact that, yes, there's always uncertainty in our predictions, and that's because we're not dealing with, these uncertainties are not random. We're not dealing with a completely random system that we can never understand or, in a sense, decrease the uncertainty. We're dealing with a chaotic system, and the concept of chaos is completely different from randomness, as I'm sure you all know as statisticians. And so I thought I would talk a little bit about how we approach quantifying the uncertainty and using the fact that there is uncertainty in the way that we make our forecasts and predictions. And of course it goes back really to Ed Lorenz, one of our absolutely most influential scientists in my field, who famously said in 1963, "One flap of a seagull's wings may forever change the course of the weather." And that's what we're dealing with, really. This is the concept that fine-scale processes, turbulence, whatever it is, right down to the very, very smallest scales and the shortest time scales, influence gradually the result that you get. And what does that actually mean for us in weather forecasting and climate prediction, and how do we handle it? And actually, you as approaching, perhaps, how do you use your statistics in these disciplines of weather and climate science? How does that influence the sort of statistics that we need to do? So that's what I'm going to cover today. Very general. Hope nothing too complicated, but it's just to give you a flavour. So when you hear somebody say, oh, the Met Office got the forecast wrong again, or the climate change is far too uncertain for us to make any decisions, you have a bit of an understanding of what we're dealing with. So what I'm going to talk about is a little bit about Ed Lorenz and the concept of chaos, and then how we look at uncertainties through initial conditions, through stochastic processes, which I'll come on to explain a bit, and why we can actually consider predicting on climate timescales. What is it about the system that allows us to do that? And then how should we represent uncertainty in our projections of climate change? And then I'll say just a little bit about, at the end, about some slightly more philosophical points about how we go from uncertainties really effectively into probabilities, because that's what we're all about. Ultimately, what my science is about is helping all of us, whether we're individuals, businesses, government, whatever, manage risk. And to manage risk, you need to know about the probability of the hazard. So, Ed Lorentz, the Lorentz attractor, simple set of equations, but they're nonlinear, and this is from his very early papers on that. And the figure just shows how in time you vary from one state to another, and if you can then see this as a multi-dimensional Lorentz attractor, the prototype chaotic model. So that was the very simple idea that Lorentz showed, that you could, with just small perturbations, move from between different states. And if we think about that more in the sense of predictability, then what the Lorentz attractor shows, that the predictability in some sense is flow dependent. So depending on where you start in that chaotic system, you can either be quite predictable or you can be quite unpredictable. This is just an example of 3 possible climates of the Lorentz model, if you like. And depending on where you start, you can either get quite a predictable solution, which is the top left one. You can get one that is predictable to begin with, and then it oscillates between 2 potentially different states, different parts of the attractor. And you can get some where there's just no predictability at all. When you start down near the middle of the attractor, you can go in all sorts of different directions. So the growth of the initial uncertainty is strongly dependent on the starting conditions. That's what a chaotic system is, and therefore the predictability of forecasts is variable. So when we think about how we make a forecast in an ensemble system, we start off with what we think the state of the atmosphere is now, but of course even that we don't know with total certainty, because we can't observe every bit of the atmosphere at the levels of detail that we need to know. So we need to sort of assume that there's some level of uncertainty in the initial conditions, and you can do that by putting tiny perturbations around your initial state and running your forecast lots of times with tiny perturbations on the initial condition. You can actually be even slightly cleverer than that and work out where you think the uncertainty will grow most strongly, so that you get a reasonable sense of the spread of the solutions at some forecast lead time. So you run a set of forecasts, and you would hope that as you go forward, the uncertainty that the forecasts diverge through the chaotic processes, through those nonlinear processes that Ed Lorentz described in his simple model, to occupy a phase space described by the darker blue area there. And you hope, and would, if the model is any good at all, that those possible outcomes lie within what we might think is the current climatology of the weather in a particular location. If they don't, there's probably something wrong with your model. It won't occupy the full range of possible states, because we're doing a forecast for a particular day. And the size of the spread of the uncertainty, very much, as I've said, does depend on the initial condition. Here's an example of a forecast for London, one on the 26th of June 1995 and one for a year earlier. In the first example, we can see that the situation probably was a high pressure very persistent weather pattern, so there's a large degree of predictability. The spread of the forecast is really quite small out to about 5 days ahead. So we have examples like this where we can forecast with considerable skill out to 5 days ahead if it's the right sort of weather regime. And I think actually we're enjoying some really nice weather at the moment, but that was been on the cards for about a week ahead. We knew that was coming. It was setting up, and we can be pretty confident of what the weather's going to be like for the next few days. Another example, which was absolutely fascinating, was the St Jude Day storm, where again the forecasts were really quite confident in picking out this storm quite a few days ahead. And then you can have other examples, such as June 1994, where we can see that the uncertainty grows really quite rapidly. And in fact, the forecast is really pretty well not good by after 2 or 3 days, that the ensemble is outside the observations. And that's, we have to understand when we do forecasting where you have good spread and where you don't have spread, and what sort of conditions, weather regimes, flows give us more predictability than others. So in other words, the predictability of the system is itself predictable. And that was something that Lorenz also talked about in his early papers, that there are certain flow regimes where you can get a large degree of predictability. Of course, here's the great storm. So, you know, Mike Fish continues, and the Met Office continues to get enormous amount of flack because of the great storm. And Mike Fish saying, as you can see, a woman rang the BBC and said she had heard that there was a hurricane on the way. Well, if you're watching, don't worry, there isn't. The trouble was that in 1987, Mike Fish didn't have the luxury of ensemble forecasting and this idea of uncertainty. He had one forecast. And he based it on that. And, of course, we all know what happened. It was an amazingly damaging storm. But, of course, actually, if he'd had the insight that we now have, because it was round about then when we really started to think about chaos as being an issue, he would have said something different. So here we are, here's 2 forecasts, starting from what appears to be the same initial condition. As you can see, this is the pressure, and if I, hopefully, it'll, oh dear, it's not going to work for me. Should do. Probably because it's on a different system. My apologies. I'm not going to be able to show this. It should link through to my stick, but doesn't. What it would have shown, if I'd been able to run it, was that over time, the evolution looks almost exactly the same. They're indistinguishable. And then, just out of nowhere, a tiny feature grows that becomes the storm that Mike Fish didn't forecast. And what it's saying is that the tiniest perturbations in the initial condition that were imperceptible to a field like that, to a forecaster, can grow and produce an explosive storm of the sort that Mike Fish had to deal with in 1987. So if he'd had, at that time, what we now produce as a routine set of forecasts, he might have said something different. So here we have a whole set of forecasts. These are from a study that was done at the European Centre, but similar things go on at the Met Office. And we can see that if we look at the top, that's actually what happened. It was a very deep low form that passed across the southern part of England with very strong winds on its southern flank here. This was a what we call a control forecast, which would have been like the forecast that Mike Fish might have had. One example. But if we look at the whole ensemble, and if he had seen this, this is 66 hours ahead, I think he might have said, uh-oh, I need to be a little bit cautious about what I say. And if we had seen this now in the Met Office, you would probably have anticipated a yellow or even an amber warning going up a couple of days ahead. So this is what we're talking about. This is what we have to do every day now to look at uncertainty. So we use ensembles of forecasts, and how we process those ensembles and how we produce our forecasts, and we talk about the probabilities, is a very important part of what we need to do. So they're about forecasting uncertainty and estimating probabilities, and they're really very useful because you can, as you saw there, assess possible outcomes, you can estimate risks and probabilities, and actually they allow you to gauge the confidence that you have in the message that you're putting out through your forecast. And of course, ultimately, we're about allowing people to manage risk. And risk is a combination of the likelihood of the hazard, but also knowing about your exposure and vulnerability. There are other steps in that process that I won't talk about today, but that's what we're dealing with here. One of the things that we found, though, when we construct these ensemble systems is that they're under-dispersive. And what that means is that the root mean square error goes faster than the spread of the forecast. And a good ensemble system where you've really got a good handle on the uncertainty, on the chaos, you should find that the error growth is overlain by the spread of the ensemble. But this is a fairly typical characteristic of most of our ensemble forecasting systems of recent years. So what it says is that the ensemble forecast then becomes overconfident. You're not sampling in a wide enough possible states to be sure that you are giving getting the right sort of assessment of likelihood. So, as I've said, there are ways you can improve that, and one of them was by identifying the right sort of initial perturbations that you add to the forecast, what we call singular vectors that give maximum error growth. That's helped a bit, but it still hasn't solved the problem. And one of the reasons that we think that these forecast systems are under-dispersive is because we don't represent the very fine-scale processes that go on in the atmosphere. The turbulence, the convection, all those atmospheric processes that are not properly resolved by the grid scale of the model. Typically, in a global model, that scale is now about 20 kilometres, and we'll see later on that even at finer scales it matters. So when you look at, here is the kinetic energy spectrum, very old figure, but actually incredibly influential figure, which shows the energy spectrum depending on the wavelength of the perturbation, or the energy where the winds are acting. And we can see that the energy spectrum is continuous. That's not very surprising. There's energy at all scales. And yet in models we have to truncate that energy spectrum by the grid length that we can resolve. And we try and represent unresolved processes through something that we call parameterization, where we try to represent the bulk effects of the subgrid scale processes using the variables on the resolved grid. And I think a lot of us have known for quite a long time that actually that this approach of parameterization is taking out some of the energy at these smaller scales that are an inherent part of a chaotic system and therefore an important part of model spread. It says, and this is a slightly more complicated point, that there's no coupling between the dynamics and what we call physics, which means things like latent heat release, clouds and so forth, on these unresolved scales. And actually the more that we understand about things like cumulus convection, we know that that's not true, that the flow at these fine scales is highly influenced by latent heat release at these fine scales, and things like mesoscale squall lines particularly in places like Africa, the big thunderstorms that we see here. There's a very intimate coupling between the flow and the storm, the rainfall, at scales that we probably just don't resolve in the model. So we know that there's an upscale cascade of energy from these fine scales to the larger scales. And this probably won't run either, for reasons that I don't fully understand. But if this had run, you would have seen how this is convection, in this case over the West Pacific, how it evolves with a multi-scale structures that show that actually there is no sort of preferred scale where that energy cascade stops. And so what we believe is that the fine scale unresolved processes, they themselves are chaotic. So this concept of a stochastic element to the way in which we represent the physics, the way the clouds form, the way rainfall forms, is an inherent part of how we should represent uncertainty in models. And at the heart of this, of course, are all the phase changes of water. And this just is a schematic of the different space and time scales of all the different processes that we try and represent in these models. And basically, if you're looking at a climate model, you're basically not really representing, except through these bulk parameterizations, anything that goes on this side of the diagram. And that's a problem for us. Similarly, a weather model is still only here. We manage to just about capture hurricanes. We certainly don't capture the big cumulonimbus properly. We now run very fine-scale process models as part of our research, and we're getting down there to more like the cloud scales, things that are happening sub-kilometre, round about a minute on the time scales. So you can see what the challenge is for us, that all this physics that's going on right back here, is it right that we represent that simply as a bulk term? And the answer is definitely no. And the more that we work with these models, we're beginning to understand how important it is to represent even this bit of the diagram in what we do with a weather model, and even more so with a climate model. And so that's where the concept of stochastic physics has come, and I'm not going to spend a lot of time on this. These schemes, there are various ways of approaching this, but it's actually trying to capture that bit of the energy spectrum that we don't resolve and represent it at the resolved scale. And this is just an example. That should be one of those, I think, unfortunately. But the idea here is that you can see that the total dissipation rate from numerical dissipation, convection, gravity and mountain wave drag. Here's an example of that forcing pattern, and you can see that it's located where we have downstream of mountains, jet streams, and we can see the areas of convection here in the tropics and the storm tracks and so forth. And when you do that, you find that actually you can actually change the whole nature of the model performance. And here's just a schematic to explain how that might be. That with stochastic parameterizations, you can change both the mean and the variance of the PDF, if you like. So here's an example where the atmosphere is sitting in some regime where if you've only got weak noise, it's just going to hang about, and you have in the end a unimodal probability function, distribution function. But actually with strong noise it's possible to shift the atmosphere into a different regime, and that's what's inherently behind this. And it's really interesting that when you apply these schemes, it really impacts both the variability of the model and increases the ensemble spread, but actually it seems to also improve what we call the systematic error, the fact that we have insufficient blocked flows in the model, that we don't capture the precipitation in the right places. So this is really interesting, that fundamentally in all of this, these fine scales really do influence the resolved scale, and so we need to think about how we represent those. And when we do that, we find that actually, here's an example from the Met Office a few years ago, that actually the forecast spread, certainly at longer lead times, gets up to agree with the RMS error. So we're managing to increase the spread, the dispersion of the ensemble in the right sort of way. Very interesting result. As well as improving some characteristics, some basic characteristics of the performance of the model. So when we go back to this diagram, and we started off with initial condition uncertainty, which was kind of where Lorenz was starting from, we can now see that actually there's a very important part of the whole system which is also about model uncertainty and the role of these unresolved energy cascades. And so we now also introduce in our probabilistic ensemble forecasting systems the concept of model uncertainty. And one of the big, I think, really exciting breakthroughs is what should that stochasticity look like? And one of the things that's been, for me, very exciting over the last few years is the fact that with increased computer power, we can now run incredibly fine-scale models, which essentially allows us to really try and get a handle on what's the time and space scale characteristics of these stochastic processes. There is a pattern to them. They're not, again, not random. They're flow dependent. They depend very much on the processes we're trying to represent. If I'd had that convection movie had worked, I'd have been able to show you the preferred scales that we understand. And so I think in the next 5-10 years, the way in which we represent the subgrid scale uncertainty, these stochastic processes, will really change quite dramatically, because we can learn from very fine scale models of the system that have immense realism, actually what is going on in that energy cascade and how does it all work. So I think it's going to be a very exciting 5-10 years as we improve our understanding of how to represent, really turn our parameterizations into probabilistic parameterizations that represent the stochastic processes that go on even down to fine-scale turbulence. So that's a bit about how we do weather forecasting. But actually, lots of people often say, when they want to get at us, if we can't predict the weather beyond the next week or so, why is it possible to make seasonal forecasts? And Ed Lorenz's papers basically said that the predictability limit for the weather was probably about a week. We think it's a bit longer than that, because there are things that give us longer memory than that. But it's a fair question. And of course, it's about the impact of boundary forcing. So if you go back to the Lorenz tractor and you put in a boundary forcing, and we'll say what that might be in a minute, you can show that the shape of the attractor and the residence times within each lobe of the attractor changes. And here's an example with different levels of forcing, and by the time you can see here that as you go through the different strengths of forcing, you completely, by the time you get to quite strong forcing, you basically don't occupy one regime for very long at all, and you spend a lot of time in another regime. And this is really interesting when we think about what this means for climate prediction. So what he's basically saying, when you look at those very simple diagrams, that again the probability function, depending on the strength of the forcing, is predictable. So when you have weak forcing, you basically don't change the number and spatial patterns of the regimes. They remain the same, but their frequency of occurrence might be changed. This is the Lorenz model paradigm, that if you're, for example, and we'll get onto this in a minute, if you have an El Nino going on, you don't necessarily change the spatial patterns of the regimes, but their frequency is changed. So if you another example that I worked with quite a lot was the active break cycles of the Indian monsoon. There are two regimes that the monsoon likes to be in, and can we work out what sort of forcing makes one regime preferable to the other? Because if the monsoon spends more time in a break situation, then you have a poor monsoon, you have big impacts on crop yields in India. All these sort of things we were trying to understand in the concept of these regimes, but their frequency of occurrence is changed. On the other hand, if you have strong forcing, then the number and patterns of the regimes may be modified as the atmospheric system goes through bifurcation points. And this is the climate change problem. By actually really forcing the planet systematically and quite strongly over a long period of time, will our weather patterns change fundamentally? So this is how Lorentz plays into our thinking about climate prediction, whether we're in a regime with weak or strong forcing. And the other thing that's really important about it is if you understand that that's what a chaotic system is about, it's not, of course, possible to say what the weather will be like at any particular place on any particular day, because we're quite clear about that, but the limit of predictability for that part of the process is indeed a week, maybe 2 weeks. But it should be possible to say what the statistics of the weather might be over the coming season or decades, and that's really important distinction, and that's why it is possible, even though we can't forecast the weather beyond a week or so, why we can talk about seasonal forecasting, decadal prediction, climate change projection. It's about saying how often will we be in one regime or another. So, in 1981, these ideas began to come to the fore, and there was a very nice paper which essentially set the stage for seasonal forecasting by Jules Charney and Jagdish Shukla, which noted that if you, in the absence of forcing, of course, most of the observed variability at mid-latitudes, but not at low latitudes, can be associated with short-period flow instabilities. So a lot of the time, you could say, in our neck of the woods, the weather does what the weather wants to do. But on the basis of available evidence, it is suggested that a large part of the low-latitude variability, in other words, the tropics, is due to boundary anomalies in such quantities as sea surface temperature, albedo, and soil moisture, which, having longer time constants, are more predictable than flow instabilities. So here we're getting into this idea that the slowly varying components of the climate system lend memory to the atmosphere in a predictable way. And the classic example, of course, is El Nino. And that was very much coming to the fore at that time. We were beginning to understand very well what the influence of El Nino was, certainly around the tropical belt, and that actually many of these aspects were predictable. So there's this concept that different parts of the system also respond differently to a forcing. So this became then part of a whole new discipline of climate prediction on seasonal to decadal timescales. On the seasonal timescale, El Nino absolutely dominates our predictions. But on the decadal timescale, we're increasingly seeing that things that go on in the North Atlantic and in what's happening to the big overturning circulations in the Atlantic can have a discernible signal above, even in mid-latitudes, above those inherent flow instabilities that Charney and Shukla talked about. So to actually exploit that memory, of course, you've then got to bring in the oceans. In the oceans, the flows are much slower. They have an enormous thermal capacity compared to the atmosphere, so it's not surprising that actually the oceans can lend memory to the atmosphere on these much longer timescales. So when we do this, we now actually initialize both the atmosphere and the ocean from observations. We actually combine initial condition uncertainty and stochastic physics perturbations. But actually one of the great challenges in this area, of course, is that during the period of the forecasts, the systematic and model-specific errors tend to grow more strongly in a fully coupled system. It's less constrained. So when we look at these longer-term predictions, we actually also have to look at the fact that the model may not actually be, the forecast may not actually lie within the climatological phase space that you would like them to. So we have to think of clever ways of bias correction. And that's where some pretty interesting statistics comes in. We often use, because of that, we often use multi-model ensembles when each model has its own error growth and its own biases, and we can use those to provide a better sample of the forecast phase space. So it's always sort of something I've slightly struggled with, that actually you can put together a set of models that perhaps are not that good and be actually apparently more skillful than if you took a single model that's quite a lot better. But it's because by using multi-models, you sample a greater part of the forecast phase space, so that in statistical terms, you appear to have greater skill. So, El Nino dominates seasonal predictability. We have an El Nino growing as I speak, a big one, and it's going to have a big impact, and it's already having a big impact around the world. And of course we understand those, but if we look at where the impacts are, and this is just a schematic, you can see that seasonal predictability is highly dependent on location. So El Nino has specific impacts, particularly around the tropical belt and across North America. But actually, when we look at UK and Western Europe, we're among the least predictable places on the planet. So I got some flack, I think, the other week for admitting that our seasonal forecast hadn't been that good this year, and it wasn't. We didn't pick up the signals of a poor summer, and it's because we're a very unpredictable part of the world. And I think, we need to understand that, and the reason we do a lot of seasonal forecasting in the Met Office is not because we want to predict just for UK and Western Europe. We can do an incredibly good job about forecasting climate anomalies all around the world that have that are really important for managing famine, for managing water resources, for all sorts of stresses on populations around the world. So again, it's this idea that not every location do you have predictability, even when you know that El Nino itself is highly predictable. And also, just as I showed for temperature for London in a weather forecast, the ocean in itself is more predictable. Different phases of El Nino are more predictable than others, and this just shows an example from 2002 of a seasonal forecast for the El Nino, an El Nino index in the middle of the equatorial Pacific, for on this side the growing phase of an El Nino, and on this side the decaying phase of El Nino. And on the growing phase, we can see that the models started in the spring, didn't really capture what actually happened very well, and they've also got a large spread. And we know that actually in spring we have what's called the predictability barrier for El Nino. It's a time of year where you can get quite a lot of forcing of the ocean from chaotic processes associated with tropical weather. We call them westerly wind events, and they can actually trigger a major El Nino or not. And depending on how we represent those, we can find we will grow an El Nino or not. And this is just a very nice example of that predictability barrier in operation. On the other hand, once El Nino is well in force, there are dynamic processes in the ocean. We call it the delayed oscillator, for those who know anything about El Nino, that actually are highly predictable. These are Rossby and Kelvin waves in the ocean that determine how the system will evolve once El Nino is well in place. And we see characteristically on this side the peak of El Nino around Christmas time, and then its subsequent quite rapid decay into the following spring. These things are highly predictable because the system is constrained through the dynamics to give you that answer. It's really important to understand when you're looking at these sorts of forecasts where you have predictability and where you don't. One of the important things around seasonal forecasting is, of course, being able to, and these longer term things, ensemble forecasting in general really, is how reliable are the forecasts. And this is one of the big problems that we have, and this is where, again, where statistics comes in, that we have to go back and forecast, run the same system over lots and lots of past cases, we call them hindcasts, to see whether, on average, the system captures the climatological frequency of extremes or not. And we can see here an example for here talking about the lower tercile. So again, we actually tend to look at probabilities of below, normal and above, slightly more nuanced now than that. And then you can actually calibrate your probabilities based on your reliability diagrams. And temperature, of course, we do a lot better with, and particularly over large domains. This is northern hemisphere temperature. But things like tropical rainfall, still fairly unreliable. One of the things that, of course, that is really challenging on this is that the observational base is not stationary either. So although you can go back over, say, the last 40 years and do your hindcast set, first of all, you didn't observe the oceans as well as then as you do today, so you probably didn't initialize your models as accurately as you do today. But also, the climate itself is not stationary because of climate change. So this is a really, really challenging problem when we think about how do we assess reliability of forecasts. So the future climatology won't necessarily lie over the current climatology. And so how do we know whether, how do we approach this statistically to know that our models are reliable when we're dealing with a non-stationary climate? I don't think we have an answer, but I think it's a very interesting question. And here's just an example. This is the UK temperature anomalies over the last 100 years or so, and what you see here is a warming trend. Now, it's not warming, we still have cold winters, but actually there is definitely a warming trend in there. And so how do we assess the reliability of our models in the context of all of that? It's very challenging. And it becomes more so when you think about climate change projections. And here we go into having to use multi-models, and this just gives you a sense of the sort of scale of the problem that we're dealing with, that we have here a whole set of models. This is the IPCC, and for the last assessment report we've got 42 climate models, not all of them running the different emission scenarios, which are the colours here, but what you've got is an enormous spread. What do you do with that? How do you get out probability, likelihoods? How do you get out reliability? It's incredibly challenging. And the IPC is based fundamentally on multi-model ensembles, and there are issues with those. There are strengths, but there are also limitations. That ensemble I've shown you is not designed to sample model uncertainties in a systematic fashion. It's an ensemble of opportunity. It's also rather small. 42 is not enough to define a likelihood curve. and there's no way, whilst it gives you a range of possible outcomes, there's no way of defining what's the distribution of possible changes, of which the multi-model ensemble is just a sample. So then again, I think this challenges how we approach working out likelihoods rather than just a range of possible outcomes. And there are very, very interesting ways of doing that using emulators, using Bayesian statistics. And part of that was done in the Met Office through what we call perturbed physics ensembles. This was an alternative approach where we can use a very large ensemble to sample the model uncertainty. So this is going back to the things I was talking about earlier on, the uncertainties in the physics, within the single model framework. So we can actually look at the uncertainty in the way that we understand the physics of these fine-scale processes and see how they play into the uncertainty in the future climate projections. It has real strengths, and I'll show those in a minute, but it also has some limitations because it's a single model at a single resolution, granularity, and it's still got some quite fundamental assumptions in how we represent subgrid scale processes. But it does allow us actually to move from uncertainty, a range of possible outcomes, to the likelihood of possible outcomes. So here are the sort of uncertain parameters we need to worry about. I've already talked a bit about convection, but there are a load of other ones. Cloud microphysics is probably the biggest one for climate change prediction, and we know that cumulus convection is probably our really biggest uncertainty in a lot of what we do. And here's an example from a perturbed physics ensemble of the sum of precipitation change in response to a doubled CO2, and we can see here why these things are needed. Here's just two examples of summer precipitation, very dry, greatly reduced precipitation over England. Here's another one which says slightly increased precipitation over England. This is the sort of issue. So if we only had a few of these, we wouldn't be able to say what's the likelihood of that one rather than that one. But with this number, we can do that, and that was the basis of the UK climate projections in 2009, where we were able to show, in this case, this is the change in summer precipitation, the central estimate, the 50%, the most likely outcome, and then very unlikely to be more than that, and very unlikely to be less than that. It changes the whole nature of the way that we can allow people to make risk assessments, to use our information, accepting that there is uncertainty, but we've quantified that uncertainty. And we've gone from uncertainty to likelihood. And I think that's a very, very important step forward. So that's where we've got to go in the future, I think. And to produce these sorts of descriptions involves not just some clever climate modelling, but actually some very, very sophisticated statistics around it. So that's one of the crossover points between what I do and what you do. But it also allows us to do a bit more than that, because actually it tells me where I need to put my effort. So we can look at where those uncertainties come from at different times in the climate change projection process. So this is the 2020s, and this is the 2080s, and we're looking at rainfall in southeast England, and we can see that it comes from natural variability, it comes from Earth system feedbacks, the carbon cycle, from model uncertainty, which we've talked a lot about, and some from downscaling from the global to the regional local scale. And you can see that the source of these uncertainties changes in time. So that in the green box, we know that if we can improve our model physics, our understanding of how clouds form, we can reduce those uncertainties. And we have very nice examples of work we've done there on that. We can reduce the uncertainty possibly in the role of the response of the Earth system processes things like the carbon cycle by greater understanding of these slow components of the Earth system. But actually they might even introduce more uncertainty. And a good example is that we now understand that the nitrogen cycle is a fundamental component of the Earth system that controls the carbon cycle. So in fact, lack of availability of nitrogen may actually inhibit the ability of the terrestrial carbon cycle to take up the carbon dioxide from the atmosphere. So the more we understand about the Earth system may in fact increase the size of that box. That's the nature of science. And then of course we can actually reduce the natural variability uncertainty through initialization. Now these were all based on uninitialized long-term projections of climate change. But actually if we initialized the system today, we could say with much greater confidence what the climate change projection would look like in 2020s. And that's the basis here of our decadal forecasting system, slightly complicated diagram, but showing a whole series in red of the decadal forecasts that we make. In black is the observations. In green is what a non-initialized ensemble of climate projections look like, starting from way back, probably at the beginning of the industrial age. And then this is our forecast in 2014, starting from the real state of the system. And we can see that the uninitialized were much warmer than we've had through what we've called the recent pause in slowdown in global warming. But the projection now is that the prediction is now that the system will warm up quite rapidly and get back closer to the uninitialized. This sort of information really important. So here we are, probabilistic predictions of climate change. We have to deal with the fact that the future climatology will not be the same as the current climatology. We've got to deal with not just initial condition uncertainty, but model uncertainty from stochastic unresolved processes and from parameters that are poorly constrained in some of our parameterizations. So in a sense, actually, Lorentz has had a very profound influence on what we're doing. He raises some fundamental questions about how much we can reduce uncertainty in weather and climate predictions. And just to finish off, I'll come back to El Nino. And this is a series of the temperature, the ocean temperature in the East Pacific from 2,000 years of simulation with a climate model. And at the top is what we know from observations. So we've got about 100 years of observations or so. And if you look at this diagram, you'd say, well, it looks sort of vaguely okay, and you might, but on the other hand, if you tested your climate model and you'd run it for 50 years and found a behaviour like that, you'd have said, this model's no good at El Nino, I need to do something about it. It doesn't look like the real world. And I might have found another one where I'd have said, well, El Nino is far too active, so the model's still not right. Or I might have found another one where I have a very strong biennial component to El Nino. And again, I'd say, well, the model's not right, it's not got enough chaotic behaviour in it. Or I might have found one that actually looked awfully like what the observations do. The point about this is that it's incredibly difficult when we get down to things, more sophisticated things in climate models, with the observational record we have, to know whether the model is right or not, statistically, because chaos produces this very rich behaviour in the system, in the observations, but also in the models. And we have to bear this in mind when we assess what model bias is. And of course, if we're thinking about what will El Nino be like in the future, then you could either have 200 years like those in the red box, or 200 years like those in the blue box, and they would be very different answers. The blue box says probably El Nino will be weaker, and the red box says it'll be stronger. The point is that the butterfly or the seagull's wings work on all time and space scales. They're not just relevant to weather, it's relevant within the slow processes in the ocean. So when we think about uncertainty of what our climate's going to do in the next 100 years, we have to think about these sorts of things. And that's why it's so important to look beyond. The observations can only give you one realization of the past, but a chaotic system can give you a multiple set of realizations. The other final example is where we're going now. And you'd think that as you go to higher resolution, the need for ensembles might go away. But it doesn't. And this is an example from our kilometer-scale forecasting model. One is a radar image, this one here, and this is a model forecast. And it's showing the passage of a cold front. Here we go, across the country. This is one of the heavy flooding events, and you'd say at first sight, this is a hell of a good forecast. But actually, if you're about managing flood risk on a particular river catchment, you look in detail at where the heavy rain rates are on an hourly timescale, they're quite different. And so even when you get down to these very fine scales, very short timescale forecasts, uncertainty is in there. The flap of the seagull's wings is just as present. So what we do now is we actually run a whole set of forecasts, even for our regional local forecasting, at fine scales. And this is just an example. It's not the same, it's almost the same period, yes, of a front, again, passing through the country. And this is the fine scale model. They've all got the front on, but they have very different ways in which it's evolved as it passes over the country and where the most intense rainfall is. And so when the forecaster uses this, then what he can do is actually produce a probabilistic forecast of where he thinks the heaviest rain will be. And this is really important because now we've gone down to fine scales, we can actually really enhance the probabilities. We can actually produce more reliable, more confident systems. So here's an example, same sort of thing, of now the probabilities of exceeding this is 10 millimetres in 6 hours. That's quite a lot of rain. That's the sort of thing that gives us flash flooding. And here, with the UK fine-scale model, we're able to pick out certain parts of the country where the probability is in excess of 40% quite some time ahead. If we'd only had the global model, we would have only got probabilities that were much, much lower. So the point here is that going down in scale also allows you, for certain applications where you're really interested in high impact events, to actually give you a more confident forecast. So this is also part of what we need to think about, is how do we use these different types of models to get down to the sort of level of confidence that we need to be allowed people to make the right assessment of the risk and their exposure. So we have a long, long way to go with this, and we're starting to apply these systems to climate change now, so that we can really say something about high impact weather in the future and what the probabilities, how the probabilities would change of high impact weather as the climate warms. So some concluding remarks. There's no doubt that Lorenz's theory of the atmosphere and the ocean as chaotic nonlinear systems pervades everything we do. Estimating and reducing uncertainty and moving to more reliable and confident predictions requires us to do a whole load of things in the Met Office and in other major centres around the world. And of course, how we actually use that information and extract value from it often involves a lot of the skills that you have. And we build the models, we look to the data analytics and statistics to help us extract value. But the fact of the matter is there'll always be an irreducible level of uncertainty, the flap of the seagull's wings, on all time scales and on all space scales. It's something we have to learn to live with. But chaos doesn't mean randomness. It doesn't mean that you don't know anything. It actually, there's a lot we can do within that framework of a chaotic system. So thank you for listening, and I have run over slightly, and I apologise for that.
A few minutes for some quick questions for Julia. There are roving microphones, so questions?
Yeah, I won't wait for a mic, sort of clear enough voice. It would be really nice to see those simulations. If it was possible to get them going on a laptop during one of the breaks, I'm sure I wouldn't be the only person who would like to see them run.
Oh, the ones that were on here. Yes, I know. I can't understand why, because I'm running it off my stick, and it ought to have picked them up.
Get them going on a laptop during one of the conferences.
Yes, I'll try and do that for you. Yeah.
Thank you. One of the themes in your talk was how the uncertainty in your forecasts is often quite variable.
Yes.
And I just wondered, in terms of managing expectations for people, the masses, everyone in society, in terms of looking at forecasts. At the moment, we just give people point predictions, I guess, for the temperature tomorrow. Would it be a good idea to give people a sense of the variability in the forecasts to manage their expectations?
Absolutely, and I think one of the things we've struggled with is how the public understand probabilities and things. And I mean, you will see gradually more things like that coming up. So I mean, if you go to your sort of site-specific forecasts, certainly with rainfall, we give probabilities. So they are there. We don't with temperature. And sometimes on the weather forecast on the television, you'll see the presenter saying, actually, we don't know whether the storms are going to track to the north of the country or to the south of the country. There are two possible regimes that the model is giving. And they kind of say, watch this space, come back tomorrow and check in again. So we're beginning to do that, but actually we should do so much more of it, because as you can see, the uncertainty is just a fundamental part. So being able to get people to think more about probabilities, just as we do in many parts of our lives, would be a great help.
There's some quite well-known long-term physical effects like solar cycles and perturbations to the Earth's axis and that sort of thing. I mean, have those been factored into all these climate models? Because I think the solar cycle typically is 11 years or something.
Yes, absolutely. And I mean, some of the recent breakthroughs we've had in seasonal forecasting for our winters have been tied up with understanding and representing in the models the processes whereby the 11-year solar cycle affects the weather regimes that we experience over the North Atlantic, Western Europe. Absolutely, yeah.
Given that you're funded by the government, do you ever come under political pressure to produce numbers, particularly with regard to climate change, that might be in a particular direction?
Absolutely not. No. I mean, it's fascinating that people. I mean, there's this idea that somehow you can get one of these climate models to produce a particular response is almost impossible when you think of the degrees of freedom in the system. And no, so. But what's been really important, I think, is this exploring the uncertainty, so that we can say to government what's the more likely outcome than just it could be anything between here and here. And I think that's really important.
Yeah, I think Julia will be around in the coffee break, and hopefully we could set up a laptop.
Yes, I don't know why that didn't work, but.
So can you join with me and thank you for being